So here's another example that was on Wikipedia, which is a wonderful example. It's kind of a famous example in this area, just to describe the numbers, how this numerically can happen. So in American baseball, a batting average, so if you've never seen or heard of baseball, baseball is a game where a player, look it up, a player goes up with a bat and the pitcher throws the ball really hard. It's really, really quite difficult to hit a baseball, especially in the professional leagues. They throw the ball 100 miles an hour. So the player swings the bat and tries to hit the ball. The percentage of, basically, not exactly, but the percentage of time that the player hits the ball is going to be their so-called batting average, right? And really good players can do this, let's say 30% of the time. Excellent players, but most players are worse than that. Okay, so here's two players and their batting average. So player 1 had 10 at-bats in the first half of the season and got 4 hits. Player 2 had 100 at-bats and got 35 hits. So the player 1's batting average was 40%, player 2's batting average was 35%. The second half of the season, player 1 got 25 hits out of 100, 25% batting average. The second half of the season, player 2 got 2 out of 10 hits, 20% batting average. So in both the first half and the second half of the season, player 1 had a better batting average than player 2. Right? However, if you just add up these numbers, 29 hits out of 110 at-bats for the whole season for player 1 and 37 at-bats for 110 for the whole season for player 2, you get 26% for player 1 and 34% for player 2. So player 2 has a better batting average. So it seems paradoxical that a person can have a better batting average for both the first half and the second half of the season, but have a worse batting average overall. But of course, the numbers work out, right? You see it. The numbers actually work out. And so, I put in consider the number of at-bats here because that's coming into play. That the player ones had this very good batting average when they had relatively few at-bats, and a modest batting average when they had lots of at-bats, and vice versa for the other players. So that's, I think, really the culprit in this case. Okay, and another very famous example of Simpson's paradox is the so-called Berkeley admissions data, and it's fun and it's in R. So I'll cover it a little bit, and you can explore it because to get it, you can just do help UCB admissions, and then that'll describe the data set. Data UCB admissions will load it up. And then here I give a little command, apply UCB admissions C12 sum. It gets the appropriate marginal. So here we looked at whether or not, so for admission versus rejected by gender, and we get that males, the acceptance rate was higher for males than it was for females, disregarding everything else. Okay, but I give another command here, and then it shows now the admissions rate. I'm not showing the counts because the table is getting a little bit unwieldy. So I'm showing the admission rates by department A, B, C, D, E, F, and E and F. And then what you can see among, for department A, males got admitted fewer percentage of the time. Department B, males got admitted fewer percentage of the time. Department C, males got, got admitted a slightly larger percentage, lower for D, slightly larger for E, and lower for F. So clearly the admissions, gender imbalance in the admissions is dependent on whether you're conditioning, the evidence of gender imbalance in admissions is dependent on whether or not you're conditioning on department. And there's different application rates, and you can explore this yourself. There's different application rates by gender for each of the departments. And so look here, in fact, you don't even have to explore it yourself. I apparently have it on here on the next slide. So gender, male, female, by department, and you can explore this a little bit more because the data is just in R. I don't think you have to have any other packages installed. You can just do data UCBA admissions and play around with it. So let me talk a little bit about what in the world is going on here, because it's confusing. It seems confusing. To me, there's a couple of things that help me understand Simpson's paradox. First thing is The math, there's no problem with the math, right? If you're saying that, A over B is less than C over D and E over F is less than G over H, but if you can find integers that satisfy the following equations, where B has to be greater than A and F has to be greater than E and so on, but if you can find integers that satisfy these equations, then you've found an example of Simpson's paradox. You just have to put context around it. But it doesn't seem at all paradoxical when you state it as a couple of relationships between integers this way, right? Then it just doesn't seem very paradoxical anymore. It's the context that adds the paradox, and just from a statistical standpoint, it says the apparent relationship between two variables can change in the light or absence of a third, which again doesn't sound that paradoxical. It's only when we conflate the probabilistic statements and the evidence associated with the probabilistic statements vis-a-vis the data with the causal statements, right? So the problem is we're going to try and get at the cause, the truth, by virtue of the probabilistic statements and the associations obtained from the data. But that's a quite hard thing. The question in all these cases is, what's the right answer? What should you condition on, or should you not condition? And that's a hard problem. We're not going to really cover that in this class. To me, the real answer of this is that it's quite hard to exactly figure out when you've conditioned enough, right? And in some cases, no conditioning is exactly the right answer, and in some cases, conditioning is exactly the right answer. To really handle this formally, you've got to do something called causal inference, basically, and that is really the discipline that's really the subdiscipline of statistics that is really entirely designed towards addressing this question in a formal manner. In the meantime, but let me say this. In the meantime, what can you do? And the idea is to not decouple the statistics from the scientific discussion. In the case of the death penalty, you would want to have a discussion about hypotheses for the causal mechanisms between the various associations. Does it make sense to be conditioning on the race of the victim? In the Berkeley admissions data, you'd want to talk about, well, are there very different acceptance rates by departments, and then are there different application rates by gender to each department? And does the fact that, say, are women applying to departments that are harder to get into? That would explain the marginal association quite well. And is that really the driver? And that's a discussion, kind of in a sense, a discussion that's informed by the statistics, but extra statistical. And at this point, I think it is this kind of interplay between the data and a scientific discussion is the best solution I can offer to you for dealing with confounding. When you take further statistical courses, you can learn some of the formal mechanisms for trying to account for confounding. But suffice it to say, it's one of the harder issues in statistics. Knowing how to balance the over-adjustment with under-adjustment in terms of confounding is one of the central problems in observational data analysis. And it's what makes observational data analysis so hard compared to, say, for example, where you randomize a treatment or something like that.